All right, I'm going to go ahead and get started while they work on that. Let me say first, thank you very much for welcoming me here again. It's an honor to come for a third time to Big Data Spain. And I wanted to congratulate also Oscar and Ruben and all the people that put this together. It is amazing having been here from the first year and seeing the first year we met in a university in Madrid. I don't remember the name, but it was definitely much tighter and cozier than this. So to walk in this morning and see 1,200 people here in this huge auditorium is it's very impressive. So congratulations on growing this and making it a great conference. And thank you again for inviting me back. So I want to talk today a little bit about some of the things about happening in the Hadoop ecosystem in the enterprise. And let me kind of set the stage of what I mean by that. Obviously, big data is a huge space. It's a little bit of a buzzword these days. Actually, it's more than a little bit. It is a buzzword, which means everybody's sticking big data on whatever they do and saying this is big data. So I want to focus down the scope of my talk. Obviously, there's tons and tons of things happening in Hadoop. I can't cover all those in 40 minutes. And so that's why I put that enterprise word in there. But I want to define that because people, at least in my space, use that a lot. What do I mean when I talk about the enterprise? I mean companies who are building things on top of Hadoop. Companies who are building applications, building their business on top of this data, just like we just heard about BBVA and all the work they're doing on top of big data. These are the kinds of people that I want to focus on. So, being one of the founders of Hortonworks, I have the privilege to kind of see both the technical side of things, what's moving in the ecosystem, and how that's being adopted out there in the enterprise, how people are using it. So I wanted to share a little bit of that with you this morning. So I thought Oscar's slide that set up the history of kind of computing or data computing since the 1970s was a great introduction to where I wanted to start too. So I also wanted to tell you a little history. I was not in the very, very beginnings of Hadoop, but I joined the Hadoop team at Yahoo within about a year of the beginnings of Hadoop. So as far as Hadoop goes, I'm one of the old guys. And one of the things about old people is they like to tell you stories about the way it used to be. So I want to start with a little story of the way it used to be. How did we kind of get here? And then use that to set the stage to look at some of those things that are happening now in the enterprise. So Hadoop started in 2006, and as I'm sure you know, at first it was really two things. It was the distributed file system, HDFS, which was a great way to store a lot of data in one file system, and it was MapReduce, one programming paradigm. And very, very quickly, a lot of other projects sprung up around this and started to work on it. And we see here kind of a sampling of some of those early projects. And as Paco referenced, when all you have is a hammer, everything looks like a nail. And it turned out that Hadoop was a really big hammer. People really wanted to hit their data problems with Hadoop. And so we saw them starting to do things that MapReduce really wasn't built to do. MapReduce is great at a certain set of problems, but there's a whole other set of problems that it's not good at. But as people started to bring all their data into one place, you could store it all in HDFS. You could process it on this massively parallel system. They really wanted to be able to apply other algorithms to that. And the Hadoop community responded to that with a new system called Yarn, which I'm sure you've heard of. This rather goofy slide is actually one of our favorite slides at Hortonworks. I don't know why Batman is slapping Robin, actually. I've never figured that out, but whatever. Anyway, the importance of Yarn was that it split out execution from scheduling, and it enabled you to build multiple executors in this system. And so with that split, MapReduce became just another execution paradigm, but you could build others. And one of the best ways to know as an engineer that you succeeded is when people build things you've never envisioned on top of what you built. That's huge validation and, frankly, a very enjoyable experience. And we saw that happen in the Hadoop ecosystem. The number of projects just exploded that could run on top of Hadoop. And this is just a sprinkling of those projects, right? If I put all the logos on the slide, you wouldn't be able, the slide would just be black. You wouldn't be able to see, they'd all be on top of each other. So we saw that growth. Now, from a technologist perspective, all that growth is great, right? It's really exciting. I know sometimes for the enterprise, it's a little bit, somewhere between terrifying and confusing. They're not really sure how to respond. There's all these things going on, all this change. What pieces do I use? What pieces are important? How can I make sense of this kind of many-legged thing, and which parts are important to me? So I want to highlight some things that are going on in this system that I think are important to the enterprise today. And I'm going to do that by focusing down. So think of this as, it's a little bit like going on a hike, and I want to be the guide that points out a few landmarks as we hike. There are many things to see in this, but I'm just going to point out a few things that I think are important. So let me start with talking about some of the tools that people are using today when they process Hadoop, or when they use Hadoop, to process their data. And I want to point out a couple and kind of use them as stand-ins for parts of the ecosystem. One of the first ones, obviously, is Hive, Apache Hive with its, and I'm using it to represent the SQL processing. SQL obviously has been around for a very long time. It's a very common way to process data. Now, it has a number of advantages. It's very easy for a lot of people to use, and it has a very mature tool ecosystem around it. Once your system can speak SQL, there's lots and lots of tools that can connect to it and that can now make use of your system. So Hive is a project that started very early in the Hadoop ecosystem, and originally it was really just a translator from SQL to MapReduce. It was for big batch jobs, because that's what MapReduce did well. But as I already said, as people got more and more of their data in here, they wanted to do more and more work with it. And they said, well, I don't want to do just big batch SQL jobs. I want to do interactive SQL. I want to be able to hook my reporting tools to this. I want my analysts who sit there and type queries to use this. I want to connect my cubing tools to this so that I can slice and dice it. Hive wasn't there yet. But it responded to that and started on a journey. So see here, Hive started out as a top-level project in 2010. 2012, it added ODBC and JDBC connectivity so it could talk to these tools. And it started growing its SQL out of the very basic stuff it supported early on to support what you would expect in a modern analytics, modern data warehouse in order to do and support your analytics. We rewrote the engine underneath Hive so it doesn't use MapReduce anymore. I mean, you can still make it use MapReduce, but now there are other options. You can use Apache Tez or Apache Spark as that engine underneath to run much more efficiently, especially for short-running queries. We rewrote a lot of the internals of Hive so that it was basically in line with modern research on databases. And we rewrote the file storage format so that it could store data in a columnar fashion and much more efficiently answer queries. And then we started putting in things like authorization and governance. And I'll talk a little bit more about those later. We also went in and added transactions. So early in its life, we didn't have transactions in Hive, and we kept saying, well, you don't really need them, they're kind of extra. And then we saw more and more customers saying, yes, we do need them, and trying to put them in there themselves. And so we went and added that. So now you can do updates and deletes and insert individual rows into Hive. And finally, well, not finally, but and this year, we've introduced what's called LLAP into Hive, which is a standing set of daemons to answer queries very, very quickly, so that we're truly moving into sub-second query range, where we can answer those queries very fast. So you see how Hive is evolving to become the data warehousing tool that people want, while still working at very large scales. I want to talk just a little bit about the LLAP stuff, because I'm particularly proud of this. It's something we've worked a lot on, and I happen to spend a lot of my time in Hive, so whenever I get the chance, I make sure and share this with people. So what is LLAP? It's the adding of standing servers into Hive so that it can cache data effectively and answer queries quickly, but we're not only using these to execute the queries. So Hive can still do the old style batch queries when you need it to, without flooding its caches, without overwhelming these daemons, because maybe your query needs to run on 500 nodes and you only have 10 daemons. That's fine. Hive still works in the traditional way you would expect in a Hadoop cluster, where it can spin up containers and run. But for those queries that need to run very quickly, especially over hot data sets, where everybody's running queries against those same data sets, LLAP can cache that and allow you to share that cache between your users in a secure way and answer those queries very quickly. And you see here a chart of comparing Hive 1 without LLAP to Hive 2 with it, and the speed up factors that we're getting. And we are starting to actually see some of those queries return in just a few seconds, and this is over 10 terabytes of data. So this is a good data size. And in fact, we're starting to see some of the queries run so fast that we're now able to execute them faster than we're able to plan them on the front end. It's actually taking us longer to figure out how to run the query than it is to run the query, which tells us where our next area of optimization and work needs to be. If you're interested in this, I'll be giving a talk later today with more information on this. You can learn, I'll go another level down into a lot of how this works and what's going on here. Now I want to shift to another tool. I talked about SQL as a way a lot of people use the data. SQL is great for a certain set of problems. But there's also, let's shift and look at the data scientist for a moment. Now these people might use SQL, but they might also use Java or Scala or Python or R or any number of other things. For those people, we see tools like Spark really being the way they want to interact with the system. This year Spark came out with Spark 2.0, which added a number of features, including better SQL support, very promising APIs with data frame and data sets. But let's take a look at kind of how people are using this. So this screenshot is from a notebook. It's called Apache Zeppelin. There are a number of different ones out here. You probably heard of Jupyter. There's some others. This is one that Hortonworks supports and uses, so that's the one I picked. But see how up in the top here, you have a little bit of Scala code that reads some data out of your system, sets up something as a table, and then these three bottom tabs, you can write quick Spark SQL statements against those and get visualizations out of it. That's the kind of thing that, or at least one of the places, where we see people using tools like Spark to do these sort of data scientist things where you have one person or maybe a small group of people, and you can share these so they can be shared amongst a group, sitting down, pulling some data out and starting to work with it and play with different things, all very quickly, all very interactively, right? And saying, oh no, that's not the graph I want to see, throw that away, or oh, that's interesting, but what if I add this filter, or what if I look at it in this way or that way? It allows for very interactive playing with your data while you figure out what's there and what you want to look at. So those are a couple of the tools that people are using, or a couple areas of tools that people are using a lot in the enterprise. Now, remember that this is the enterprise. These are people who have data that they have to secure and they have to govern, right? And what all does that mean? Obviously, security, part of security is making sure only the people who are supposed to get to see the data. But that actually turns out to be a reasonably complex problem. It's not just, Alan can see this or Alan can't. There can also be nuances to that. Maybe I can see part of the data, but not all of it. Maybe if maybe at my work I could see the employee table. I know everybody who works there, but I can't see the salary table because I'm not in accounting, so I don't get to see, the salary column. So that, when I read data from that table, that column should not be there or should be blanked out. Or maybe there's data that you need to encrypt so that even if you're storing it, day-to-day people can't see it unless they have specific authorization to go see that data. We also see people wanting to do even more interesting security type things. There are companies that have rules that data can only be accessed during certain times of the day, say during business hours, to prevent their employees from logging on at home and pulling down data they shouldn't be pulling down. There are obviously location-based policies. Many countries have laws about not taking data outside of the country if it's generated there. So you may have a system sitting in Europe and a system sitting in the United States, and if those systems may be able to talk to each other, but if the user's in the United States, he may not be allowed to access that data that's in Europe because he's not allowed to export it. Even if he were located here in Europe, he would be able to see it. There's even certain prohibitions on things you can do with data. In the United States, we have a law around healthcare data called HIPAA, and it controls what you can do with the data, not just in terms of who can see it, but even the types of results you can get back. And I'll give you an example. Let's say you have a relatively sparse rural area where not a lot of people live. There are certain types of queries you can do where even if the data underneath, or even if the data that you're querying doesn't include personal information like names or addresses, if there's few enough people in the area and you apply a strict enough filter, you might be able to reverse engineer who those people are. If your query, say, returns less than 100 results, and that actually is, those sorts of things are actually in this law, where you can't, in certain times and places, you can't return results from queries if the data set's too small, because you could reverse engineer that and figure out who the data refers to, even though it doesn't have personally identifiable information. So you have to be able to prohibit those types of activities as well. A query that might be allowed until you see the results, and suddenly you have to tell the user, I'm sorry, I can't give you this result. And then obviously there's prohibitions on particular data types, like what we call personally identifiable information, names, tax ID numbers, those sorts of things, where if you know that information, it's very easy to figure out who this person is or track them down. How do you do that? You have all this data in a big place. You need to secure all that. So an example of this are a couple of other Apache projects, one called Apache Ranger and one called Apache Atlas, that work together to do this. Ranger is able to apply all those security policies I just talked about based on time, prohibition of certain actions, personally identifiable information, location of the query, all the query generator, all those sorts of things can be managed by Ranger. Atlas is actually a data governance system that deals with understanding what's in your data, metadata not from a runtime perspective, like a data catalog in a database, but metadata from a user perspective of understanding how your data relates to each other. So it can do a lot of things like show you how two data sets are related. But one of the things that it keeps track of is what of this information is PII, personally identifiable information. What is, how do these two data sets relate? And that can be used by Ranger to understand what it should and shouldn't prohibit. So we see users in the enterprise very interested in these security and governance solutions, because these are the things they need to make their, one, to make their applications work, and two, to meet the regulations and privacy concerns of their users. All right, I've talked a little bit about tools and things that are happening now. I want to change direction just a bit and talk about a little less about tools now and a little more about kind of things I see influencing where enterprise use of Hadoop and friends are going. So 5 years ago, even 2 years ago, the stress in data processing was get the data into your central warehouse as quickly as you can, whether that's a traditional data warehouse, such as Teradata, whether it's Hadoop, whatever. The idea is get the data there as quickly as you can, minimize that time lag to get the data to you, and then start processing it. That, I think, is changing with the advent of streaming tools and other things. We don't want to wait until that data gets to the central warehouse to process it. And let me give you a couple examples of how this can work. First, there's data at what we call the edge. This means where the data is being generated. And a good example of this is aircraft engines. So if I have my stats right, I'm working out of my head here, so I might mess the numbers up slightly, but I believe this is right. A modern aircraft engine on a jumbo jet generates 2 terabytes an hour of data, just watching itself, how it's running, and all that kind of stuff. So that means, now when you fly from the west coast of the United States, where I'm based, to here, it's about a 10-hour flight. So that means each engine on that aircraft is generating about 20 terabytes of data. And there's, depending on the aircraft, 2 or 4 engines usually. So that's a lot of data, right? Now, all that data is of some value, but obviously you can't, no airplane has the 100 gigabit uplink or whatever, and even if it did, you couldn't move that kind of data in that amount of time to move all the data from all the engines, because it's not like the engines are the only thing happening on the airplane, right? There's other things generating data. What does all this mean? It means you have to decide which bits of data to upload and which not. What's important out of that? Not to say you'll throw the rest away, because when the plane lands and you can plug it into a cable, you can download the rest of that data. But some of that data is important now while the plane's flying. Like, is the engine working efficiently? Is the oil pressure proper? All those sorts of things that relate to, is the engine going to keep going while we're flying? Versus just, is it performing optimally? Is the fuel efficiency where we want it? That data you can download later, because it's not going to affect this flight if the fuel efficiency is off by 5%, right? So you have to make that decision about what data do we send up. And so we see projects like Apache NiFi, and just to be clear, it doesn't work inside jet engines yet, so I don't want to give the false impression there. But you see projects like NiFi that are working on, that allow you to put that at the edge and decide what data matters here. What should I send up versus what do I keep? But it isn't always, the data flow isn't always unidirectional. It's not just I want to send that data up. Envision, still using that aircraft example, envision that some data starts coming through that the system on the ground that's watching that data, making sure the engine's going okay. Envision that system has some questions and it isn't sure whether the engine's okay or not. And it wants to say, send me a little more data from this time. It needs to send a command back the other way to tell the engine, hey, send me the next level of detail for the last 5 minutes, because I want to see whether you're doing okay or not. So the data flow needs to actually be bidirectional, and this is something that projects like Apache NiFi can manage. So that's kind of where the data gets started. It starts on this edge, and it moves up into your regional and core infrastructure. And then it often lands in a stream, like Apache Kafka, where it can be processed by projects like Apache Storm or Apache Spark. Any of these things that you'd use to do your, or Apache Flink, or any of these other streaming things that you use to process your data. But again, this is a place where I think it's changed. In the past, those tools were focused largely on, let's just get the data moved into the warehouse, and more people are starting to ask, what queries can I do on that data while it's in the stream? How can I transform that data so that it's already ready to be queried when it hits the warehouse, what you might call continuous ETL, or in the querying case, continuous analytics. This is really driving a change in the way users interact with their data and the latencies they're seeing. All right, oops, that was not what I was expecting to happen. There we go. A last area of big change, the cloud. Obviously, the cloud is not new. Cloud's been around a long time, and every few years, the cloud's going to take over the world, and then it kind of doesn't for a little bit. So I think we're back in the cloud's going to take over the world phase. I don't think the cloud's going to take over the entire world, but I think more and more, well, I certainly see more and more our customers saying to us, we're going to do new things in the cloud. I don't know how many of our customers are saying, you know what, we're going to build some stuff on premise, we're going to keep what we have on premise running, but all of our new stuff is going into the cloud. Hadoop has run on the cloud since pretty much day one. At Hortonworks, we have almost our entire history run all of our tests in the cloud because for the same reason everybody else does. We can't afford all the hardware to run it on-prem. But Hadoop doesn't necessarily, the cloud hasn't always been Hadoop's best home, let's put it that way. There were a lot of things in Hadoop that assumed it was written to work on premise. So one of the big areas I see changing the Hadoop ecosystem today is moving to make Hadoop more at home in the cloud. If an elephant riding a cloud is a natural image, which it really isn't, but that's all right. So why are people moving to the cloud? Why are customers coming to us and saying things like, I want to build new stuff out in the cloud? Well, there's really a number of reasons we see that our customers saying this to us. Probably the biggest is time to market, if you will. How long does it take when I decide to start on a new application before I can start running that application? I don't actually know what it's like here in the European market, but in the US market, on average, we find from the time someone says, I want a new Hadoop cluster to the time when it's actually available is often 6 to 12 months. By the time you rent space in a data center, buy hardware, pay somebody to wire up the hardware, pay somebody else to install the operating system on the hardware, then come in and put on Hadoop, then get your application put on there. There's just a lot of waiting and lining up there. In contrast, on the cloud, everyone in this room, well, the network would probably crash, so maybe not everyone, but you could, before the end of my talk, have a cluster up and running on one of the clouds. Like it's pretty straightforward to get started very quickly. This is particularly useful when you want to test out a new idea. I don't know if this is going to work or not. And it's hard to go before your boss and justify, yeah, let's go buy this big cluster and rent space in a data center and sign a 3-year lease, and I don't even know if this is going to work. Versus I can go to Amazon, try it out, go, yeah, that's a great idea. Let's build it out, or no, that was not a good idea. Let's not do that. So that time before you can get stuff up and going. Related to that, obviously, is no upfront hardware costs, right? You don't have to spend money up front to do that build out. Now you're gonna pay the same amount of money. I don't think cloud's gonna save you tons of money in terms of total cost, but it is gonna allow you to amortize that cost over the time you're using it instead of all up front. Things run a little differently in the cloud, which has some upside too. In a traditional Hadoop cluster, you tend to build one large cluster and you try to make sure everybody can fit into it, and it needs to run a long time. There are some advantages to doing this, some reasons to do it that way, but there are also some advantages to saying, you know what, all my data is stored in the cloud, and I'm just gonna bring up a cluster that's very specific to what I wanna do when I need to do it, and then when I'm done, I'm gonna turn it off. That allows you to tune your cluster much more efficiently for your particular task, and it allows you to only pay for the hardware when you're actually running a cluster instead of 24/7. And then finally, one of the obvious benefits of cloud is the unlimited elastic scale, right? In the United States, most retail businesses do almost half their retail business in November and December because it's in preparation for the Christmas season, right? So obviously their hardware needs are much higher in those months than they are in June and July when people are all on vacation from school and not at the store buying new clothes or TVs or whatever. So you get this kind of radical swing in the hardware needs. The cloud adapts very naturally to that. You don't have to have your hardware sitting, you don't have to buy at the peak November, December level and leave a bunch of your hardware sitting idle the rest of the year doing nothing, just so you don't crash during the all-important Christmas season. So that's great. Moving into the cloud, what does this mean for Hadoop? When you shift the platform that a system sits on, you're going to shift some of the assumptions the system's built with. So what does that mean? It means that we have to build Hadoop to work with in shared data and shared storage, right? It means that it has to handle these on-demand ephemeral workloads well. You need to share metadata and security and governance. In the cloud, you get naturally all your data stored together, but you want all that metadata to stick with it too, and that's something that today the clouds don't provide. We need to add that. And Hadoop needs to be able to handle this elastic resource management well. So, as I said, with shared data and shared storage, now the data storage is segregated from compute. You get Geo Distribution from free, but you need to handle the fact that your data storage is not necessarily local to your system anymore. That means you need to be much more intelligent about your caching. LLAP that I just talked about as big cache can really play well here for Hive, where it can cache that data very efficiently because the difference between reading out of memory and reading out of the object store is very significant. HDFS can be used to cache as a front for S3 in the same way if you're using HDFS on your local nodes. As I've kind of already referenced, by having these ephemeral workloads, you can tune clusters to exactly what you need to do. If you want to do data science, maybe all you need in that cluster is Spark and Zeppelin, nothing else. If you want to do data warehousing, maybe you just need Hive with LLAP, and you're good. Maybe you're going to build an ETL cluster that's Spark and Hive or some combination thereof. Whatever you build, you want all these to share that same metadata. You want one central metadata system that knows where your tables are, what security requirements they have, what governance is on those, where did that data come from, how is it moving through there. This needs to be kind of always on for you in the cloud, even if you're not paying for the compute to run. Obviously, it should turn itself off when no one's using it, but it needs to be there and a durable part of your system. Now, this is an area where I think Hadoop is going to have to adapt even more, is learning how to manage workloads, not just based on available capacity, but managing to your budget. Are you going to miss an SLA, but there's spot instances available? It should go grab, and you have budget, it should go grab more instances. Are you going over budget, but you've got extra capacity? It should start releasing things back into the pool so that you're not paying for them. To finish off the cloud thoughts, I don't have a slide on this, but I wanted to point out too, Hortonworks obviously works in the cloud. We've worked for a long time on HD Insight on Azure, and you may have seen, I think it was 2 days ago, we announced our Hadoop in the data cloud in Amazon, where you can do these ephemeral clusters that are specific to various workloads, where we have data warehousing, data science, and ETL as cluster types that you can stand up, pay just for what you use, and shut them back down, all in a nice GUI, so that you're not having to install the cluster and all that stuff. You go to the system, say what you want, spin up the cluster, do your work, shut it down, and it's all good. So where's the end point of this? Where is this pointing toward? At the beginning of my presentation, I said I use the word connected data architecture, and I think that's where we're heading. People will have data on premise, people will have data in the cloud, they'll have data that's in motion, data on the edge, in their data centers, which is what data at rest here means. All those are going to be connected. You're going to be working, you're going to be using data from all those points, doing data science, doing queries against those. In fact, we'd like to get to a point where you as a user may not need to worry about where in this admittedly rather goofy looking slide your data is, right? You should just know, oh, I need to read this data, run my query, and the system can find that data for you and run the query against it. But that connectedness, where you have data in all these places and you're moving it around as need be, is what we see as where the Hadoop ecosystem is headed over the next few years. With that, I'm finished. Thank you very much.